In part 1 of this tutorial, the concept of convective steering was introduced, as well as capillary action and the two withdrawal rate regimes, the convective and advective regimes. Here we will discuss how to increase the strength of convective steering to increase the density of particles deposited on a surface. Basically anything that increases evaporation rate will increase conductive steering. The faster solvent molecules leave the meniscus through evaporation, the faster solvent molecules will move from the bulk solution towards the meniscus to replace those that have left. This generates a flow that carries solutes and suspended particles towards the drying line. Perhaps the easiest way to increase evaporation rate is increasing the temperature of your chamber. For instance, when we have a low temperature, the convective steering towards the drying line is low, and so particles will just be brought back into the bulk. However, when we force evaporation, we're going to force the particles to be stuck at this drying line between the drying meniscus and the substrate. When they're pinned like this, then they deposit. As an example, we can see that at low temperatures, around below 40 degrees, and low deposition rates, we'll have thick particle depositions. And if we increase the withdrawal rate, of course we go back towards this intermediate regime that we talked about in part 1. And so the film will become thinner and thinner as we increase the rate of withdrawal. Now if we increase the temperature, what might we expect? We would expect that we would have thicker films at faster withdrawal rates. So there's this play between the withdrawal rate that we withdraw our substrate and the temperature of our ambient environment. To quantify this, these authors looked at changing the withdrawal speed as a function of temperature, and they show that there is indeed this relationship between thicker films as we increase the temperature. Instead of increasing the evaporation rate, we can simply increase the concentration if we have particles that are easy to concentrate. Here's an example from my lab, where we tried depositing particles that were suspended at a dry weight percent of 0.1%, 0.5%, and 5%. The bare substrate is a darker gray, and the particles are the lighter gray, so we can see some contrast in these images. And we can see that as we increased the concentration of the particles, we were depositing more and more. Around 0.5%, we had a pretty nice coverage, a monolayer coverage. At 5%, we started to get a lot of multi-layer coverage, so we can still see parts of the substrate that are bare, but this is just because we have thicker depositions of particles. So this is one way, but if we're working with particles that are expensive or precious or we can't make huge quantities, increasing the concentration isn't a good solution. That's why people will use instead temperature, which is exactly the same thing. We're concentrating our particles, but we're only concentrating it in the meniscus. Another way to increase conductive steering towards the meniscus is to change the humidity. We all know that when we wash our clothes and hang them out to dry, on a very high humid day, then the clothes will take a lot longer to dry than if it's low humidity, we're in the desert. The same is true for films, for thin films. If humidity is low, there's going to be a lot of evaporation, and so the particles are going to be brought in high concentration and with speed to this drying line. If humidity increases, the flow towards the meniscus is going to slow down and eventually stop, which means that the particles, if the humidity is high enough, can even leave the particles that have already been deposited. They can go back into solution and return into the bulk. So it's important to think about this when we're working with thin films. A film is dynamic. There's vapor coming into the film as it dries as well as leaving, and we have to control the environment in order to control the quality of our deposition. Many people noticed that there was a homogeneity problem with their thin films, so they didn't necessarily understand why. For instance, in this film that has the drying line here, the initial original deposition started here, and then the film was withdrawn, so this is the end of the film at 8 centimeters. And what can be seen is that the thickness started out around 160 nanometers, and as the film was withdrawn, it got thinner and thinner to reach a thickness of around 45 nanometers. This is a really common problem, and this is related to humidity, but not really humidity, it's actually solvent vapors. So when the film is plunged into solution, we can see that in the reservoir, the meniscus will creep up. So there's a lot of airflow around the meniscus as deposition begins. As the film is withdrawn, however, the volume that was displaced by the film allows the solvent to drop into the reservoir. And this space doesn't have as much airflow around it, and thus it becomes saturated in vapor pressure. And so this buildup of solvent is going to slow down the evaporation dynamics of the film, which accounts for this decrease in the thickness of the film. We can see this a little bit clearer in this example where the authors deposited 3 different films. One was mesoporous silica in ethanol, which has a pretty high boiling point. And as a function of speed, the thickness changed severely. So at very slow speeds, we can see in blue, there was a homogeneity problem. As the speed increased, the film became much more homogeneous in thickness. When we went to a solvent, water, that had lower evaporation rate, so a slower buildup of solvent vapor, we can see that the speed had less of an impact. At speeds of 1 millimeter per second and 5 millimeters per second, we had homogeneous films. And if we went to a solvent on the other extreme, THF, which evaporates much more easily than ethanol, no matter which speed the authors used, they were incapable of making a homogeneous thickness across their film. So we have to think about 2 factors, the solvent volatility and the withdrawal speed, which will impact the homogeneity of the film thickness. I'd like you to spend a couple of minutes thinking about how this can be overcome. There are a couple of solutions, so you can think for a little while. Please pause the video and restart when you have the solutions. 3 solutions which I came up with were to use very fast withdrawal speed coupled with a non-volatile solvent, to start with a reservoir that is only partially filled, maybe only halfway filled. That way we already have the thinnest possible film, and to use a very large reservoir with respect to the volume of your substrate so that less of the solvent volume is displaced during the deposition. Which solution you choose to create more homogeneous films will depend on how much solution you have, how precious your particles are, and exactly how much surface you need to cover. Another thing to consider in terms of convective steering is the contact angle, because we need to pin the particles to the substrate. When we have solvent evaporation and the particles come in and the solvent angle is low, ideally between 15 and 65 degrees, these particles will be pinned and we'll manage to deposit them. However, when the contact angle is higher, then the particles will just be scraped across the substrate. Why is this? Well, the force pushing the particles into the substrate is always perpendicular to the meniscus. So in this top example with low contact angle, we can see that the particles are forced downwards. Where when the contact angle is higher, we can see the force is actually more horizontal than it is vertical, which accounts for the reason that the particles are not pinned and not deposited. My student Lina El Saidi showed us how contact angle can be used in order to change the density of particles that she deposited. In this case, she's depositing particles on an already nanostructured surface. We can see the particles are the brighter points in these 3 images. We can see that she changed the contact angle from 45 degrees to 30 degrees to 0 degrees. And we can see that there's a very clear augmentation in the quantity of the particles that she deposited. In her case, she wanted around 30 degrees in order to force her particles into these pores. So how can we change contact angle? It depends on your solvent. If your solvent is polar, for instance, water or ethanol, you might need to make your substrate more hydrophilic. The easiest way to do this is to use a UV ozone treatment. Here, Lena, she treated with different quantities of time. So at 0 minutes, she had a natural contact angle of 45 degrees. If she treated with the ozone for 5 minutes, then she had a contact angle of 30. And if she treated for 15 minutes or longer, she had a contact angle of 0. Her substrate was perfectly wet and couldn't measure the contact angle. However, if you don't have access to UV ozone treatment, an alternative is to oxidize your substrate in 3 molar nitric acid. Just wash your substrate really well and then put it in the nitric acid for at least a half an hour or several days, and then you'll have a nicely oxidized surface. If you want to change your contact angle and your solvent is apolar, then you need to use a different strategy. For instance, if your particles or solutes are suspended in toluene, dimethyl ethyl ether, or another organic solvent, you might need to make your substrate more hydrophobic, not more hydrophilic. In fact, we can do this by surface functionalization, and the first step will be to make your surface more hydrophilic. So use 3 molar nitric acid to treat your surface, get your surface very clean, and then you can use vapor deposition to put hydrophobic molecules on your surface. For instance, we can see here this hermetically sealed flask. So it's an airtight container. I put in my oxidized clean substrate here, and we put in a vial containing a few drops of silane precursor. Which silane precursors do we use? We can use, for instance, this silane precursor that's functionalized with a phenyl group, or we can use this methyl triethoxysilane. You have to be careful to stay at a temperature much lower than the boiling point. If you start to evaporate too much of your solvent, it's going to deposit in droplets on your substrate. This is not good. Also, you want to stay below the flash point of the silane precursor, because if you have a spark in your oven, then you're going to perhaps have a fire. Once you've allowed it to be in this airtight container at a warm temperature, such as 90 degrees in the case of this phenyl substituted silane, or at room temperature for this methyl functionalized silane, then you're going to want to rinse abundantly your surface with a dry organic solvent to get off any excess molecules. And in this way, you'll have a nice monolayer all over your substrate. Before I conclude, we're going to do some exercises to think about what we've learned. For instance, if I have this substrate with poor coverage of particles on the substrate, what can I do? Please pause the video while you think of solutions. You can increase the concentration of the particles in solution if your particles are cheap and easy to make, easy to scale up. You increase the solvent volatility and you work at low withdrawal speeds in order to concentrate your particles in the meniscus, or you adapt your withdrawal rate. You can either go very slow or very fast. In our second example, if we have poor packing, we have nice density of particles on our substrate, but they're very disorganized. What can we do to improve this? Please try and think of 2 solutions. One is you can increase the conductive steering via evaporation rate, using higher temperature, lower relative humidity, or a more volatile solvent. Otherwise, you can decrease the polydispersity of your particles. Let's say your particles don't deposit on the substrate. What can I do? You can change the contact angle, making your substrate either more hydrophobic or more hydrophilic. Or you can increase the viscosity of your solvent and work in the faster withdrawal speed regime. The thickness of my film is not homogeneous. What do I do? You can make sure that your colloidal suspension is stable, no aggregates. You can increase the withdrawal speed, or you can think about vapor pressure that might be building up during the deposition. To conclude, nanoparticle density and film thickness are affected by many parameters. These include the concentration of our solution. Ideally, if we're depositing copolymers, we're going to want a concentration of around 0.5 weight%. and for nanoparticles, we'll want to be around 2 weight%. We need to think about the withdrawal rate, where thicker films are deposited at very slow and very fast speeds. We have to think about the deposition temperature, the solution volatility, and the contact angle. Thank you.